Welcome back to the deep dive. Today we're looking at a stack of source material you brought in, and it details one of the most incredible feats of engineering out there. We're talking about the world of liquefied natural gas carriers, LNG carriers.
We are. And this is truly high-stakes territory. I mean, LNG is fundamental to the global energy supply chain. But at the same time, it is one of the most hazardous things we transport across our oceans. The safety framework is just, it's intense and frankly fascinating.
Exactly. So our mission for this deep dive is to go way beyond just, basic shipping facts. We want to really understand the advanced engineering, the hyper-specialized training, and just the sheer resilience it takes to carry a cargo with this genuine dual hazard. It's not just flammable. It's kept at a temperature that can literally shatter steel.
Right. It's a testament to human ingenuity, really.
Yeah.
We're looking at how these vessels are engineered not just to handle risk, but to actively outsmart disaster.
Okay, let's unpack that dual challenge then, starting with the cargo itself. We know it's LNG, so it's mostly methane. But what state is it in, and why is that so dangerous?
So to put it simply, we're dealing with a liquid that's been cooled to approximately minus 162 degrees Celsius.
Minus 162?
Or minus 260 Fahrenheit.
Yeah.
It's an astonishingly low temperature.
Okay, here's the question that I think everyone has right away. If the risk is so high, why that extreme cold? Why not just use a giant freezer and keep it at, I don't know, minus 50?
It's a great question, and the answer is pure physics and economics. That extreme cold is what reduces the volume of the gas by a factor of over 600.
600 times smaller.
Exactly. Without that, ocean transport just wouldn't be viable. It's that need for efficiency that creates the entire hazard profile we have to manage.
And that extreme cold leads right to the first major hazard, cryogenic danger. I assume we're talking about more than just frostbite.
Oh, much more. The risk of immediate severe cold burns to human tissue is very real. But the truly critical danger is something called brittle fracture.
Brittle fracture.
Yes. If that LNG touches standard steel, like the ship's hull, the steel loses its strength and ductility almost instantly. It becomes dangerously brittle.
You're saying the hull could just snap?
Precisely. The best analogy I've seen is if you dip a chocolate bar in liquid nitrogen. It becomes so rigid that it just shatters when you touch it.
Wow.
That's the effect we have to engineer against. It's why they use specialized materials like nickel steel alloys or aluminum, things that can handle those bone-chilling temperatures.
Okay, so that's hazard number one. What about the other side of the coin?
Hazard 2. Flammability. The vapor cloud.
Right. If containment is breached, the LNG rapidly vaporizes. It turns back into a gas. And because it's initially so cold, it's heavier than air. So this cloud stays low, hugging the deck or the water. As it drifts and mixes with the air, it warms up and enters its flammable range,
Which is
roughly between a 5% and 15% concentration of methane in the air.
So it's like, the dry ice effect you see at a concert. That low-lying fog.
It's a great comparison.
But this one is invisible, and if it finds an ignition source, it's potentially explosive. That is the nightmare scenario. You could have a flash fire, or if the cloud has settled in a confined space, a vapor cloud explosion, a VCE. The entire design philosophy is built to prevent that.
So with stakes that high, the solution has to be literally built into the steel. Let's talk about that engineered shield. How do they lock the stuff away?
Safety is by design, as they say. The structural integrity is the absolute first line of defense. And our sources point to two main types of cargo containment systems.
Right, the membrane tanks and the Moss-type spherical tanks.
Exactly. Membrane tanks have multiple barriers, and they're integrated right into the ship's inner hull. This design uses space really efficiently.
Okay, and the Moss tanks.
Those are the massive, obvious spheres you can see above the deck. They're self-supporting, structurally independent, and they're highly resistant to sloshing the movement of the liquid inside.
That makes sense. But does the integrated design of the membrane tanks make them, more complex to maintain than the big spheres?
It definitely adds layers to inspection and maintenance, which is why the operational protocols are so meticulous. But no matter which system is used, every modern LNG carrier has a double hull.
An extra layer of steel.
A second shell around the cargo area. And it's that added redundancy against a collision or running aground.
Okay, so you have these passive defenses. But what about the automated systems? The ones designed to react faster than any human possibly could?
This is where the detection systems are key. You have gas detectors everywhere. Cargo areas, void spaces, constantly sniffing the air for methane.
And if they find something?
They don't wait for an order. The system automatically activates the emergency shutdown systems, the ESD.
It just cuts everything off.
Instantly. It's designed to rapidly isolate the flow of cargo, stopping a leak at the source before it becomes a major release.
What about pressure? I imagine that's a huge issue too.
It is. And for that, they have high-integrity pressure protection systems, or HIPPS, another automated fail-safe that prevents pipes or tanks from overpressurizing and rupturing.
The idea of those systems just kicking in on their own is pretty incredible.
They are the last line of technical defense. Now, moving past prevention, let's say a fire does somehow start. I'm guessing water isn't the solution.
You're right. Water is basically ineffective on an LNG fire. You're trying to put out a burning gas, not cool down a liquid fuel.
So what's the primary tool?
Dry chemical powder systems, DCP. It deploys under pressure and rapidly smothers the flames by interrupting the chemical reaction of the fire itself.
And the water systems. They're just for
cooling. You spray water on the deck, on the bulkheads, on adjacent structures to keep them from failing from the heat and stopping the fire from spreading.
Right. And to prevent that flammable mix inside the tanks in the first place, they use inert gas.
Correct. By filling the empty space in the tank with an inert gas, something with almost no oxygen, you remove one of the three elements needed for a fire.
So you can have the fuel, but no oxygen to burn it.
Precisely. Okay, we've covered the engineering, the steel, the sensors. But these ships are only as good as the people running them. Let's shift to the human element.
Absolutely. No matter how advanced the tech is, it all relies on people following procedures meticulously.
And these are governed by things like standard operating procedures, SOPs, and planned maintenance systems.
Yes. Every single task, from a simple valve check to high-risk work like welding, requires a strict permit to work. Nothing is left to chance. Everything is documented and authorized.
So when you look at the industry's history, what's the hero story here? How have they managed to avoid major catastrophes?
What's really fascinating is that the LNG shipping industry has maintained this remarkably strong global safety record. And that record is the hero story. It's built not on being perfect, but on a culture of learning from every single near miss.
Can you give us an example? How does a near miss on one ship improve safety for everyone?
The sources mention early issues with cargo sloshing in partially filled tanks. In rough seas, the liquid would move around and create these huge, unexpected forces on the tank structure.
And these were near misses, not disasters.
Right. But they were reported openly. That led directly to new operating rules about minimum fill levels, and it actually informed major design changes in the next generation of ships.
So that transparency is actually baked into the safety system itself, which means the training must be absolutely top tier.
It has to be. And it goes beyond just the technical skills. Increasingly, the focus is shifting to what they call non-technical skills.
Like leadership, communication. How do those prevent a leak?
Because human error is still the biggest factor in most maritime incidents. You can have the best technology in the world, but if the crew can't communicate clearly under pressure, especially across different languages, or if they lose situational awareness, that ESD button might as well not exist.
And this is where technology comes back into the picture, but for training.
Exactly. They use virtual reality and augmented reality systems. Crews can run through these incredibly immersive but risk-free emergency simulations.
Like a multi-point leak and a fire at the same time?
Yes, or a complex port emergency. It lets them hone those decision-making skills in a safe space.
Okay, let's move to the active emergency itself. A leak is confirmed, the ESD is active. What's the main challenge in managing that invisible gas cloud?
The main challenge is that the threat is now invisible, like you said. So the first step is called atmospheric dispersion assessment.
Which means what in practice?
It means continuously monitoring the cloud with fixed and portable detectors to map out how big it is and where it's going. Wind speed and direction become the most critical data points you have.
And they use that data to set up safety zones.
Right. They define these zones where any and all potential ignition sources have to be eliminated. The whole goal is to make sure that flammable 5 to 15% mixture never ever finds a spark.
What if they can't stop the leak right away? How do they mitigate that cloud?
They use their water spray systems. Again, not to put out a fire. They use massive curtains of water spray to create a vapor barrier.
To push it away.
To push it, to dilute it, and to help disperse it. It keeps the gas from reaching dangerous concentrations near the ship's structure.
And what about the human risk we mentioned? The cryogenic burns? What happens if a crew member gets exposed?
It's treated as a critical injury, very similar to severe frostbite. The medical teams have specific training for cryogenic burns, which are different from thermal burns. And of course, anyone responding has to wear specialized cryogenic PPE, insulated gloves, face shields, the whole suit.
Okay, worst case scenario. A major collision. The ship's integrity is threatened. What are the evacuation protocols?
They are incredibly detailed. The first priority is a rapid damage assessment and getting everyone accounted for at their muster stations. The crisis plan has to prepare them for launching lifeboats away from any fire or vapor cloud, which is a huge challenge.
So you have this world-class engineering, these meticulous procedures, but no system is perfect. What are the systemic challenges that still exist?
The sources highlight two big ones. The first is communication breakdowns. You have multinational crews, different languages, different cultural approaches. In a high-stress moment, that can cause dangerous confusion.
That makes sense. And the second one?
Interagency integration. If an incident happens near a port, the crew suddenly has to coordinate with the local Coast Guard, port authorities, environmental agencies. And all those different groups might have different protocols, which can slow down a response when every second counts.
So connecting this to the future, where is safety headed? Is it about stronger steel or smarter systems?
It's definitely moving towards smarter systems. Predictive maintenance using AI and sensors to spot a failure before it happens is huge, but that creates a new risk.
Cybersecurity.
Exactly. Protecting the ship's operational technology from a malicious attack is becoming just as critical as protecting the steel hull from an iceberg.
This brings up a great question for you, the listener. Imagine you're on one of these ships at minus 162 degrees with this volatile cargo. Knowing everything we've just discussed, what's the one thing you would want to have with you?
It's a great thought experiment. And based on our sources, the industry would give you two answers. The first is personal, proper cryogenic PPE to protect yourself. But the other, maybe more important answer is systemic, a very good, well-rehearsed emergency manual. Because knowing the procedure is what saves everyone.
That's a fascinating distinction. Okay, for our overall takeaway, can you synthesize this whole safety framework into one final image for us?
I can try. I'd say operating an LNG vessel is like carrying a massive, freezing cold birthday cake through a crowded, unpredictable party.
Okay.
The engineering is the sturdy box that's protecting the cake. The procedures are the carefully planned path you're walking through the crowd. And the crew is trained not to trip, because if that cake drops, the party's most definitely over for everyone nearby.
That perfectly captures it. And to wrap up, the source material notes that this all requires more than rules. It requires a safety-first mentality, where even small near misses are reported and learned from.
It does. And that leaves us with a final thought for you to consider. In your own work, whatever your field, where are the critical near misses? The small things that, if they were openly discussed, could prevent a much larger systemic failure down the road. The future of safety really does rely less on new steel and more on that kind of cultural resilience and transparency.
Food for thought. Thank you for joining us on this deep dive. We'll see you next time.